Now, once we have determined that something is a function, then we rename it and use what's called function notation. Basically, this just tells the reader that, hey, this is a function. You don't have to check it. You know that each input will have only one output. Now, one example of a function that we haven't looked at yet is actually the linear equation y equals 2x minus 3. It's a little bit harder to determine if equations or functions. You have to really think about them. And you want to think about, well, if I plug in something for x, is there any chance I could get two answers? So if you think about this equation here, if I plug in x is 1, well, 2 times 1 is 2, minus 3 is -1. So just one answer, right? If I plug in x is 4, 2 times 4 is 8, minus 3 is 5, just one answer. So is there any way that I can multiply something by 2 and then subtract by 3 to get two different answers? And no, we can't, right? So you do have to think a little bit about equations because there are some where you could get two answers. Linear equations in general are not one of them. The only exception are the vertical lines, but otherwise the others are all going to be functions. So this is a function, and we do want to tell the reader now that, hey, this is a function here. So what we do to rename it is we replace the y with f of x. Now, f parentheses x is read as f of x. That's how we say that. Nothing is being multiplied. This is the biggest mistake students make is they see this notation. We all know parentheses mean multiplication, and they start multiplying everything by x. That is not what this means. This is definitions, right? This is just a notation. So this is simply notation and renaming to tell everybody that, hey, this is a function. So what happens is take that y equals 2x minus 3. Instead of writing y, replace it with f of x. Y and f of x actually are the same thing. I like to equate it with the idea of using dr for doctor in front of somebody's name, right? So let's say you're going to a doctor's appointment, right? And I don't know, your doctor's name, it will just be generic. We'll say John Smith, right? Now, normally he just goes by John Smith, we'll say, but in the doctor's office, he's probably Dr. Smith, right? Now, he's not two different people. He's the same exact person he is, whether he's home or out or in the office. But in the office, we use the abbreviation DR to let others around us know that, hey, this is the doctor, right? But the person themselves doesn't change. They're the same person, it's just a different title. And that's what we're doing here. It's the same equation. It's going to graph the same way. It's going to work the same way. It's just different notation. So how do we use the notation? A lot of things we like to do with the function is to evaluate. So evaluate just means to find the value of something here. So we have the function notation, and I want to find something like f of 4. Now, this does not mean to multiply everything by 4. So in the notation, notice how the x value is inside. The inside number then is the x value. So this is telling the reader, hey, plug in the number 4. So what I do is I take the right side of that equation, that 2x minus 3, and I replace the x with 4. So 8 minus 3 is 5. So f of 4 is equal to 5. Now, this here is your x value. This output is your y value. So this is actually the same thing as having a set of points, x comma y. In this case, it would be 4 comma 5. So function notation and points are interchangeable. It's the same data, it's just written in different ways. Let's try another one. So here, our inside value is -5. So we're saying, hey, the x value is -5. So I go back to my equation. I replace the -5 this time. 2 times -5 is -10. And I get -13. So f of -5 is equal to -13. This is the x value. This is the y value. So this is just like having the point -5 comma -13. So we actually could graph these very easily, just like we do regular graphing. Now you could also plug in different things. They don't have to be numbers. So here you're going to replace x with the expression 3a. So I take my 2, multiply it by 3a, and then do -3. 2 times 3 is 6, so I get 6a minus 3. Now I can't do anything else here, so I'm just going to leave it. So f of 3a is equal to 6a minus 3. And I'm not going to write this one as a point just because it would not be very helpful to me, but you could if you wanted to. Now we can just take this idea right here and apply it to graphing. So with graphing functions, there's really nothing different as well. So what I could still do is make a table of points, right? My y values are just my f of x values. And I could still just plug in numbers here like I normally would. Notice it's a square, it's not a linear equation, so it's going to be a little bit more complicated. I probably want at least 5 or 6 points. But I can still do the same process, right? I could pick -2 for x and then just plug it on in. So if I do some work here off on the bottom, right, x equals -2, what I'm actually looking for is f of -2, but there's nothing different in the process. I just plug in -2 into the expression. -2 squared is +4, and I get my output of 5. I can pick -1. So again, f of -1 would be -1 squared plus 1. -1 squared is 1, and 1 plus 1 is 2. Let me move that up a little bit for you, and so on. So I can still pick all these values to plug in. I choose 0, and I get 1. I choose 1, and I get 2, and I choose 2, and I get 5 again. And you can try those couple at home. And when I graph this, C2, 5, going to get a nice U-shaped graph. We're going to see and learn in this class that whenever you have squares as your highest power, you do get these U-shaped graphs. They're called quadratics or parabolas. And that's my graph. So there's nothing new here with graphing functions. If you don't like the function notation, you can always change it back to a y, and it's the same exact process. One thing I do want to note real quick, I'm going to move back up here for a second, is sometimes you see things that look like this. So in our examples here, we were plugging in the 4, plugging in the -5, etc. So sometimes you could take your function, and instead of it being written like that, they may give you something like this. F of x equals 10, not f of 10, right? So instead of putting the 10 in the parentheses, they made it equal to. That's not the same thing. These are different things. So when this is the case, they're basically telling you the y value, and they want you to solve instead 10 is equal to 2x minus 3. So again, this may not come up at all, or if it does, it may just be occasionally, but I do want to point it out that, these are different things. So our x value is 13/2 here. So you can still graph this, right? This is still the point 13/2, 10, but it's f of 13/2 is equal to 10, not f of 10 is equal to 13/2. So you just want to be a little careful here with notation. When the value is in the parentheses, you plug it into the expression. If it's equal to, then you set it equal to. So there are different little differences in notation there. Now, we've been working with a few different functions, but we haven't discussed yet how to determine if a graph is a function, right? We looked at sets of points. We looked a little bit at equations, but we haven't looked at graphs yet. And actually, this test is really helpful with equations too. So if you have an equation that you're not sure is a function, I would graph it and then do this. So this is another way to deal with it. So to determine if a graph is a function, it's what's called the vertical line test. Basically, you draw a bunch of vertical lines through it, and you see if it hits the graph more than once. If the graph touches the vertical lines more than once, then it is not a function. So what happens is basically that repeat x values occur when the vertical line touches the graph more than once. Remember, and this means that it's not a function. All right, so for the first example, right? So here's my graph. It's the U-shaped graph. It would continue on as well. And I just draw some vertical lines through it. So if I draw one here, it doesn't touch it off. It's fine. If I draw one here, it touches the graph once. If I draw one here, it touches the graph once. If I draw one here, it touches the graph once. So I draw a bunch of vertical lines through the graph, and I see that it only hits the graph one time. So something like this is a function. We will often say that it passes the vertical line test. Over here, right, if I draw a line here, it's fine. If I draw a line here, it's even fine, right? It only hits once. But if I draw a line anywhere else, like right here, it hits once, twice, right there. So if it hits more than once, this is not a function. We say that it fails the vertical line test. And what's happening here when you hit more than once, if you look, this is the 0.53, and this is the 0.5 negative 3. So you're getting the same x, two different y values. And that's what's happening with the vertical line test. So that's another way to check if something is or is not a function. And again, for equations, sometimes the easiest thing to do is to take that equation and graph it using technology and looking for the vertical line test. If you're having trouble figuring out if an equation is a function or not, graphing it is one of, I think, the best strategies that you can use. Now, finally, with functions, we can also determine the domain and range. Now, domain and range is the same exact definition with a functional relation. There's no change there. But I do want to point out there's some things we want to watch out for. And I mentioned I would talk about this. So with equations and with domain, there are two main issues we watch for. There are other issues, but for our class, the kind of beginning issues are the following ones. So one, we cannot divide by 0. And 2, the inside of a square root cannot be negative. If you do, it's not bad, but it's not a real number. It's imaginary. So we only consider the domain and range to be real numbers. So for here's my function, and this also works for equations. Notice in the first example, I have a denominator, right? So I need to make sure my denominator is never 0. I cannot divide by 0. It's undefined. So what I do here is you actually solve. So I would take my denominator, I would write it, and I would set it equal or not equal to 0 and solve for x. And I see here that x cannot be 2. If I plug in 2, I would get a 0 in my denominator. So for my domain then, it's all numbers x such that x is not equal to 2. Now this is more formal set notation here where you have the squiggles and you have the starting variable. Sometimes we'll just be lazy and we'll just write it like this instead too. You can also write it in interval notation. So how do you skip over just a single number? Well, you write it like this. You go from negative infinity to 2, and then from 2 to positive infinity. I use parentheses on the 2, which allows me to skip over it, right? Because parentheses don't include the end value. And then what you do is you put a little u in the middle, and that u basically stands for a union, which means unite, to unite the values together here. So that's really what we're looking at there. In our next example, notice I have a square root, right? So the inside of a square root has to be non-negative. So it has to be greater than or equal to 0. So what I do for these is I take the inside of that root and I literally set it greater than or equal to 0 and I solve. So here I can add 4 to both sides. So x has to be 4 or bigger. So for my domain, x such that x is at least 4, or if we're being less formal, just x is greater than or equal to 4. In interval notation, our smallest value is 4, and then it goes off to positive infinity. It is being included, right, because it's equality, so it's going to be a bracket, and then infinity always gets parentheses. So that would be the interval notation way. For the last example here, if I look at my equation, and we've seen this one already, actually, I don't see any denominators. I don't see any roots to worry about. I don't see any issues. So the domain here is all real numbers. or negative infinity to infinity. Now, one last thing I want to point out in this video is I'm using f of x, g of x, h of x. You can use any letter you want. They still all represent function notation. We usually use F because F stands for function, but you can't name different things. I guess you could name different things the same thing, but it'd be really confusing, right? So I have 3 daughters. If I named them all Sarah, for instance, I could, right? But it would be really confusing to call Sarah and have all 3 of them come running, right? So that's why we use different letters here, just to give them different names. So if I was talking about them, I could say, hey, look at the F function, or look at the g of x function, and you know which one I was talking about. So again, these tend to be the more common letters, but you can use really any letter you want with that of x notation to still represent functions.